In today's video, we're going to take a detailed look at what exothermic and endothermic reactions are, understand how to represent them clearly using reaction profiles, and finally talk about the role and importance of activation energy in making chemical reactions happen. This topic is one of the most interesting areas in chemistry because it helps explain why some reactions give out heat and light, while others need energy to get going. Now, the key idea you need to understand first is that all chemicals store energy inside their bonds, but not every substance stores the same amount. Different chemicals have different amounts of energy locked within their chemical bonds. For example, take the reaction between methane and oxygen, which forms carbon dioxide and water. Each of these substances, methane, oxygen, carbon dioxide, and water, has a different level of energy in its chemical energy store. What really matters to us is comparing how much total energy is stored in the reactants compared to how much total energy is in the products once the reaction has taken place. In this particular example, the products, carbon dioxide and water, have less stored energy than the original reactants. That difference in energy tells us something very important about the type of reaction taking place. Let's represent this using a reaction profile. On the y-axis, we show the total energy of the molecules, and on the x-axis, we show the progress of the reaction from start to finish. On the left, we place the reactants, and on the right, the products. Because the products in this reaction have less energy, we place them lower down on the diagram. The drop in energy between the reactants and products shows how much energy has been released to the surroundings. Remember, energy can never be created or destroyed. It can only be transferred. So when the chemicals in the reaction lose energy, that energy doesn't disappear. It is released to the surroundings, often in the form of heat. That's why in this reaction, if we carried it out in a closed container, we would notice a rise in temperature as the reaction releases heat energy into the surroundings. Reactions that release energy like this are called exothermic reactions. All exothermic reactions have one thing in common. They transfer energy to their surroundings, usually as heat. Common examples of exothermic reactions include combustion reactions, where fuels burn in oxygen to produce energy, neutralization reactions between acids and bases, and oxidation reactions, such as when metals rust or react with oxygen. These are the types of reactions that make things feel hot because they're giving off energy. Now, let's look at the opposite type, endothermic reactions. In these reactions, instead of releasing energy, the system takes in heat energy from its surroundings. That means the surroundings lose heat and become cooler. A classic example is the breakdown of calcium carbonate into calcium oxide and carbon dioxide. To make this reaction happen, we must supply heat energy, perhaps by using a Bunsen burner to heat the solid calcium carbonate until it decomposes. If we were to draw a reaction profile for an endothermic reaction, it would look quite different. Again, the reactants are on the left and the products on the right. But this time, the products are higher up on the energy scale because they contain more energy than the reactants. The difference between the two levels shows how much energy has been absorbed from the surroundings. Instead of being released, as in the exothermic case, this energy goes into breaking bonds and forming new ones, which is why endothermic reactions usually feel cold or require continuous heating. So far, we've discussed what exothermic and endothermic reactions are and looked at how we can show them using reaction profiles, something you'll often be asked to draw or interpret in exams. But there's one more crucial concept to understand, and that's activation energy. Activation energy is the minimum amount of energy that reactant particles need in order to successfully collide and react. You can think of it as the energy barrier that must be overcome for the reaction to begin. Even in an exothermic reaction that releases a lot of energy overall, you still have to give the reactant particles a small push to get them started. That's what the activation energy represents. We can show activation energy on a reaction profile by drawing a curve that starts from the reactants and goes up before dropping down to the products. The highest point on that curve represents the point where bonds are breaking and new bonds are about to form. The difference in energy between the reactants and that peak is the activation energy. So even in an exothermic reaction, you'll always see a small hump on the graph. That's the energy needed to get the reaction going. In contrast, endothermic reactions also have an activation energy, but the hump is usually much larger since they need even more energy input from the surroundings to start and continue. If we wanted to show what happens when activation energy is higher, we draw the curve a bit taller. If it's lower, the curve would be shallower. This helps visualize how catalysts work by lowering the activation energy, making it easier for the reaction to happen. Finally, when drawing a specific reaction profile, instead of just labeling the diagram with reactants and products, it's even better to include the actual chemicals involved. For example, instead of simply saying reactants and products, you might label the graph with methane and oxygen on the left and carbon dioxide and water on the right. This makes your diagram more complete and scientifically clear. And that's everything you need to know for understanding, explaining, and illustrating exothermic and endothermic reactions, reaction profiles, and activation energy, the three key concepts that explain how and why chemical reactions exchange energy.